Good work.
Yeah, it does.
Good.
Flawless.
I think we got some of the tech problems sorted out. Where is everybody?
Good question. What time is it?
7:28.
Okay. Nope, give them 2 or 3 minutes.
Yeah, yeah, that's
I'm just
good.
gonna get everything started.
Yeah, that's good. A couple minutes, yeah.
By the way, good games today.
I'm not sure.
Well, it took you a while to get started. I don't know the name.
So you got the one with Pam, so.
Yeah, I don't know.
July.
It's down to like-
Yeah.
Yeah, I meant to ask about switch. Now I can also meet people.
Well, can you also do that on YouTube? If anybody's creating problem.
There's nothing they can do. They don't have any access. There's a chat.
But for instance, if they leave their mic, they're not connected, they're not really connected.
No, they're not. They don't.
Okay. All right. I'm not tomorrow.
No. Next one. Next one.
Honestly. It's frustrating. Who's on, you just reach out.
Or, you know, accomplishments, like, oh, like the event, whatever.
Yeah, right here, four is a charm.
Abolished slavery, and whatever. And it's like, and it's like, okay, this was people that
Homemade ginger cookies.
say,
You want-
With real black glasses.
progressive, whatever, it's like, they were
And
the
the
ones
secret ingredient.
We're getting some audio come through.
like,
If everyone can mute
they
your
were on the,
mic.
like, let's look to the future. And you're stuck on, like, oh, let's not do that. But it's like,
We have audio coming through. If you could mute your mics, everyone, please.
They did the guy by a shock absorber. So, yeah, so I was there all morning and then they got the point. We're going away for a couple of days on some business, so I'll do it that bundle, but I was like, "Damn, the day that it's happening."
Ah,
You doing okay?
ah, ah. Hello. Ah.
Good. We hope to see more.
Yeah, no, I definitely.
At the,
Westchester this time.
Okay.
So fancy.
Come to any of our.
I definitely think it. Then also.
Sorry.
I'll put you on screen too.
Been done.
I was expecting about 3 or 4 of those 10s full.
You want to come up and do this?
Want me to do it?
Yeah. Yeah, after Dave does the intro.
It's like when you go to the restaurant and you put the food in your mouth and the waiter comes over, how is it?
Yep.
I got
After
cookie in my
Dave
mouth.
does the intro, I'm gonna turn the camera to aim right here, okay?
So you want me to stand over there?
Well, right in front of the computer if you want, or here, but I'll turn the camera so people can see.
Yeah,
you
you
can
stand over here.
Yeah, don't go too far, because this is the mic here.
Oh, okay.
So you don't want to go, don't go.
All right, I'll
over
just stand
there.
here on the computer now.
Okay.
You got an intro?
Yep. For everybody out there in virtual land and especially the folks who showed up here, welcome to the April session of the Chester County Astronomical Society. Still feels like winter out there, doesn't it?
Yeah.
Like this.
So,
I don't know about you guys, but I'm getting a little tired of freezing my butt off when I go out to observe the sky. I want this stuff to go away. Couple of things. First off, a special thanks to Dawn Miller, who made these delicious cookies. So all you out there in virtual land, don't get these delicious homemade ginger cookies. One of the advantages you have when you come to these meetings And,
Kathy's got milk.
and we have a great meeting set for tonight. It's always fun when our own, members get up and do the meetings, and it's always a special place. When I was program director, they were always my favorite meetings. So, without any further ado, let's get into it. Are we going to do it? Yes, Don Miller is gonna talk a little bit about what's up in the night sky this month.
Okay, good evening, everybody. So just go through what's happening this month. Did anyone catch the partial eclipse at the end of last month on the 29th? I was up before the sun came up, standing out there waiting for it. Nice cloud came over just as it was coming up. By the time it cleared the cloud, I got a little nibble was off the sun, and that was all I saw. So no one in the room, no one online. Okay, I was the only person. All right. Here's the details on the moon. We've got basically full moon coming up here pretty soon on the 12th, and then the new moon on the 27th. One thing is on Earthshine, which is also called Da Vinci Glow sometimes. This is when you look at the moon when it's a partial lit moon, but you can see the dark side of the moon really well. This time of year is really advantageous for that because the tilt of the Earth is now swinging around from our perspective towards the sun, and yet there's still enough ice and snow in the northern climes that they're reflecting a lot of light. So it actually lights up the dark side of the moon really well. It's called Earthshine. So enjoy it, point it out to your friends. Planets, Mercury's greatest elongation is going to be on the 21st in the eastern sky. So you're going to have to get up early to see this. Venus, 2 conjunctions, one with the moon, one with Saturn, dates shown here. Mars is getting further and further away and fading. Jupiter is going to be setting early in the evening sky. So if you want to see Jupiter and the moons, try to hit it early. Saturn's in the morning sky and starting to come up there. We just reached the ring crossing plane, so there's not going to be much to see on the rings. It's going to be just like a little line at this point, but it's always cool if you can point it out to people. Uranus in conjunction with the moon by month's end. So if you want to catch Uranus, get it early this month, not at the end. Binocular highlights. We've got, I just listed some double stars, Mu Boötes and Nu Boötes. Both are yellow whites. One's a little different shade of yellow than the other. This is a finder chart. Let's see, we have a laser pointer on here.
Yeah.
Which one is that one? Nope. I knew I was going to hit the wrong button. Oh, the top one.
Yeah,
Okay,
there you go.
there we go. Sorry. So here's Mu and Nu. And don't forget Corona Borealis right here would be where T Corona Borealis would be. Still hasn't had its climax yet. So we're hoping for that to come, but it could come in 2026. You know? Kemble's Cascade is a cool one to see. That's located right here. It's a nice binocular one, so you can see a whole string of stars going across there. It was actually, does anyone know, Don, you're pretty good with these asterisms.
I think my favorite.
And it was only found, the guy only named it, what, in the late 1990s or something like that? Yeah.
And then there's a open cluster at the bottom of it.
Yep.
Could we see what Don is pointing at? Because we can't see this, we can't see his screen.
Let's see, you see the screen now?
Or you could point on the computer screen
Oh, I
with
could probably do it on the, can you see
with
it on
a
the
pointer.
computer?
Yeah.
Is that my pointer showing?
Yep.
Yeah. Yeah,
Okay, so here's Mu for Boötes, and then here's Nu. So those are the 2 doubles, just off Boötes.
Yeah, okay, I see.
Yep. It's kind of small, the cursor is small, sorry. And then Corona Borealis, if you can see it right here, I'm moving it. This is about where T would be. So right now it's still at 10, the last I checked. So hopefully that's going to come. And then Kemble's Cascade here, you can see Perseus. So it's just off to the side here in Chemopodartis, or however you say it. I always say Chemopodartis. Yep. All right, I was close. Okay. Tongue twister there. But anyway, so here's where it is. So observing events, we're having trouble with weather. You know, you won't believe how much work goes into planning these things and, you know, coordinating with the park department, this, that, and everything. I'm going to have washout. So the red lines, cross those off. This coming Saturday, we do have at Exeter Library a solar observing session. So we'll see if the weather looks good. Roger's already predicted no, but let's see. Roger's really good at these forward predictions. He's like, I haven't even looked that far out. He's like, it's going to be bad. So we'll see. So that then we have the BRCA on the 25th, hopefully. And then we're actually going to do a fun thing here on the Schuylkill River Trail. This is a solar observing event on the 26th. So this is another one of like remember I talked to you guys about doing a sidewalk astronomy. So this is essentially sidewalk astronomy where we'll be set up along the trail. And so anyone who wants to come out and help with that, Roger is going to have a lot of great gear there. I'm going to bring one of my scopes. Anyone who wants to come. So we have more the better on that one. And then let's see, we've got the West Goshen Star Party coming up on the 3rd. So I just wanted to point that out since that'll be before our next meeting. So we definitely want to consider that. And I'll be putting out notes to remind people. Then the 5th, we have another solar event at the Middletown Free Library. So I think those were the updates for the observing. Any questions?
Thanks, Don.
Okay.
Flip the presentation over.
Okay. Okay, Don, any other business from any?
Nope, nothing for me, you know.
Yeah, you're on.
Yes.
Okay, it should be all set. You got a mouse here, Roger, and you got the pointer. Lasers, they want to just beneath the screen.
Right.
And so the camera is aiming about where Bruce is. Okay.
So hi, everyone. As always, it's a pleasure to introduce our speaker tonight, Dr. Roger Kennedy. As Dave mentioned, it's great to get a variety of speakers, but it's always nice when we have someone who's part of the society come and speak, and Roger's been a longtime member. And as you just heard from Don Miller, there's been a number of solar observing events that we've held recently. A really good one we had was March 18th right here on the Commons of the Westchester University. And as Don told you, there's a number of them that are planned in the coming month. And so it seems only fitting with Roger and the group that we should definitely have a good talk about the sun. So just to introduce Roger briefly, for those of you who don't know him, he's been an science educator both at the secondary and the university level for over 50 years, which is pretty impressive. After an internship at the Very Large Array in New Mexico, he joined the NASA MER Spirit mission and was providing science outreach programming for the Lodestar Astronomy Center in Albuquerque, New Mexico. Subsequently, he affiliated with the International Charles Bate Solar Astronomy Project while providing outreach education for the Solar Dynamic Observatory. He and his wife both provide outreach education programs for a variety of NASA's heliophysics programs. So the HEAT program, the Parker Solar Probe mission, and the recently launched PUNCH mission. And an amazing statistic, he has done over the past 15 years, approximately 1,500 programs that have engaged close to 200,000 children and adults. So yeah, really spectacular.
I feel it too.
Yeah, right. And actually, at the March 18th event we had at Westchester, I was talking to his wife, and she said, since they've retired, they've really slacked off. So now they only do about 75 events a year. I'm like, holy cow. But anyway, so it's a real pleasure to introduce Roger. He's going to give us a talk on, excuse me, bringing solar science to the general public. Thank you.
I thank you, sir. Good evening, everybody. I don't see myself, but I hope you guys can, right? So the idea is, I've given this talk to a lot of groups like ours throughout the United States. And because most people think about outreach, they think about going out and looking at the moon or, nebulae and all sorts of things like that. So when I first started doing solar outreach, we really had to up my game, because at night you've got all sorts of different things to look at. You can, look at a planet, or you can look at a star and things like that, and really don't need a lot of information about that object. You say, I've been able to find Caldwell 7. Let's look at Caldwell 7, and people go, God, I can't believe you even got it. When you're doing the sun, you've got one object that you're talking about. So you really kind of have to do a little research and learn about the object that you're going to talk about, because they look through your scope and they really want to know what it is that they're seeing there. Okay, so the presentation I got is based upon questions that we picked up over the last 30 years. People would come up to the scope and they would seem to be interested in what's going on. And they would ask you a question, and if you weren't kind of ready for it, you'd have to, be able to explain what it was that they were looking at. And you don't have to really go into a lot of detail, okay? Because average, you got somewhere between 1 minute, 3 minutes with the average visitor. So you've got to get in there, find one thing that you really like, or what's on the sun that day, and just go with it. You don't want to be feeling bad that you're not expert in heliophysics. Okay, that's not warranted when you've got a 5-year-old that comes up and says, "What's that red ball?" You don't need to go into a lot of big science thing. One day when we were at the Nuclear Museum in Albuquerque, 2 French-speaking people came up, and so I said, okay, well, I'm going to have to explain to them all about what we're looking at. So I started my little spiel about electrons giving off light and stuff. And the woman said, "We're from CERN." Okay, we know all that, but we have never seen the sun through an H-alpha telescope, a hydrogen alpha telescope. So we're looking at, the first ionization state of hydrogen. They have never seen it. They were in there blasting things apart, finding, particles and things. So I said, okay, let me step back a little bit and, go with the person that's standing there with you. Okay, listen to them, and you can kind of get an idea how far you're going to go with it or what they're really interested in. So this concept, bringing solar science to the public, has come out of a grassroots mission to be able to educate people about the sun. Okay, I'm going to learn how to do this. There you go. Okay, the first question. If I look in your telescope, I'm going to go blind, right? And I say, yes, I really like to blind 200,000 people. I take that into consideration when I'm doing these programs. Well, no, because we have state-of-the-art equipment, and we want you to be able to see the sun and do it safely. But there is a concern. You need to kind of stress people. My telescope is not a normal telescope. Yours is a normal telescope. So do not ever look at the sun with your telescope, because you end up with a hole in the back of your head. Not a good idea, right? So there is a reality of trouble with your eyes. Okay, so you have to have special kind of eyewear if you're going to look at the sun directly. Okay, you can have, whoops, I don't want to do that. I want to do this. This is a pair of sunglasses, which you do not want to use when you're going to look directly at the sun. They're good for just kind of a glance, okay? Or when you're driving your car to get any kind of ambient light out of your eye, because you're going to get a full spectrum, but it's just reduced by the sunglasses. It's still going to hit the back of your retina, okay? So to look at the sun directly, you're going to need a solar telescope with a special filter, or you're going to need the special solar glasses that we gave out for the eclipse. And I saw every student in the Kennett School District before the eclipse this year, or last year. and we gave out about 3,800 solar glasses to the kids. And then the day of, the superintendent says, we don't want them looking at the sun, they might get their eyes hurt. So they gave the glass to the kids as they got on the bus to go home. Nothing during the school time. Okay, so Rainbow Symphony is the one I do business with. They're out of California, a really great guy. And I was working on grants. So what he would do is he would match my grant. So if I had $1,000 for glasses, I got $2,000 worth of glasses. Really a great bunch of people there. Okay, here we go. So what's the word? It's called photic retinopathy. Okay, it's an actual medical condition. If you look directly at the sun, or a reflection off a metal, or if you're a welder, or if you do any work around high intensity lighting. Okay, so retinopathy is a serious situation. Okay, most of it is permanent. There are some cases where people will do this quickly, and all they do is kind of burn their retina, but not totally. And it can wear off, but not usually. Usually, when you look through a telescope or binoculars or something, you only got 10 seconds. So when I tell people, if you look up now and you see the sun, you're going to look away. That's the natural reflex. Well, you will not go blind just by looking at the sun briefly. Looking through a pair of binoculars briefly is dangerous. You'll burn your eye. So retinopathy is, this is what happens. Whoops. This is what happens to your eye. Okay, and most of that is permanent. Okay, sometimes it's total blindness. Sometimes it's just a black ball in your vision. Okay, but we don't want to have anybody have that. So always use a solar filter. I use a Lunt solar telescope, which does not use a filter. It basically deals with optics. There are 10 plates of glass in my Etalons, and what they do is they diffract light, and only one wavelength of light hits your eye, and that's red, hydrogen alpha. And the amplitude of that wave is reduced by what we call a blocking filter that's in the eyepiece. And it's perfectly safe to look at the sun. Okay, but other companies have different ways of doing this. So before you take it out, you practice on it and see what the shortcomings of the equipment that you have. Okay, where do stars come from? Where did our sun come from? Well, they're formed in a gas cloud, a long time ago. Starts moving around, it comes together. Okay, a lot of pressure develops, and a number of stars are formed at the same time. There's an association of stars that form at the same time, but then they're kicked out of that little nursery and they go other places in space. Kind of a favorite doctoral dissertation is finding our sun's siblings. So everybody's running around looking at star clusters, trying to match the chemistry of those stars with the chemistry of our star. It's really usually a wild goose chase, because by that time they're all separated. Some have met a bad end, but they're separated all over the in our case, our galaxy. And this is a star forming region in Ophiuchus. It's a James Webb image. So all the cool stuff as far as stars are concerned is coming down here. Okay, so that's where our sun came from. A star forming region. Okay, so when you're doing your research and you want to find out where stars are being formed, look for star forming regions and you'll get a whole bunch of information. They think that our star came out of an open cluster because globular clusters are generally fairly old, and there's no stars forming. Well, there are some stars forming in globular clusters, but it's because of collisions, not because of the natural process of developing a star. So our sun developed in an open cluster, very similar to the Pleiades. And once these stars really started being, a full-fledged star, because of angular momentum, it just spun out of that area, or it got kicked out by one of its brothers or sisters. So generally, you're not going to find a star like ours sitting around where its siblings are. Okay, where is our star? Okay, when will our star blow up? I can't believe how many times I'm asked that question. When will our star blow up? Okay, well, our star is now halfway through its adolescence. Okay, we have a fairly young star, only about 4.5 billion years. Okay, for some stars that are really, really big, okay, they're gone by now. Our star is a long-lived star, and it's got a long way to go in its life. So if you hear on the news that our sun's going to blow up, that's wrong. You still have to do your homework. Okay, so there's a long time before our sun gets too big that we can't live here. Okay, Yeah.
Presentation mode somehow.
what we got?
You're in the editing mode, not presentation mode. You lost the slideshow somehow. That's just stop the share and share again.
Okay, hold on for a minute.
Oh,
Did I hit
somehow
the wrong
you
thing?
hit something here. You hit something there. Let me get rid of this.
Did I do one of these down here at the bottom?
Maybe, let me just,
Okay, I could sing a little bit here if you want me to.
let's, let me stop the share and start it again. Somehow you got out of the presentation mode.
Sorry, folks.
We were seeing it just fine.
Yeah, but it was not in the
Not in the
right mode.
room.
No, it was fine in the room, but it would not advance.
It was just the slides,
Yeah. Let's try it.
It wasn't a
again.
slide show per se.
Yeah, it was in edit mode when I saw it, last saw it, that one, yeah.
Now I'm just get out of this mode.
Oh, I see what you mean. Yeah.
Huh.
Okay, now you're back in.
All right.
I'm not sure what you hit, something.
Okay,
that should advance
I'll have to
here,
tell my
don't
thumb not to
advance
do
there.
that.
Yeah, I'm not sure what happened,
Yeah, okay.
but now you're back.
Well, anyway, we have a adolescent type star, and it's got a long way to go before it gets to that stage where it's going to start getting bigger, okay, which is about in this area here. So we're at 4.6 billion years. Okay, we have to start worrying about our star in about 6 to 7 billion years. So, like I said, you still have to do your homework, right? So, what happens to a star like ours? Well, as most people know, our star will become a red giant, which means that it'll start to grow. Okay, the Earth will be in its atmosphere, like right about here. Okay, the edge of this will be somewhere between Mars and Jupiter. Okay, so that's as far as it goes. After that, our star will just evaporate. It will not blow up. It's too small. So when this outer ridge evaporates, it'll become a white dwarf, and most people are familiar with that term. So a white dwarf isn't as big as a sun is now, but it'll give off a lot of light. Just won't give off a lot of heat. There are some people that are thinking that this time frame here is the life of a white dwarf, that life on our planet could actually reach the start. Maybe not intelligent life, but some kind of life. So our sun has a long history ahead of it. Here we are right here. Okay, we've got people say, well, how do you know what you know about the sun? Well, there's a number of ways. The one that we have right now is the Parker Solar Probe is going into about 3.6, 3.7 million miles from the surface of the sun. Okay, so we have direct information from the sun because of Parker Probe. And we're learning new things every day. And the problem is it's very technical and it's not going to be in the popular news. Okay, you're going to have to wait for the journal articles to come out or somebody to do a talk about the sun itself. I'm not going to go into too much science about the sun. I want you to get the idea, the kind of thing that you would say to a person that would come up to you and say, let me look through your telescope and see what I can see. Okay, but Parker Probe, there's a lot of information about it. It's going in and out of the sun's atmosphere, but it won't get any further closer to it than about 3.5 million miles. It sounds like that's a really far distance, right? But we're 93 million miles away from the sun, and that's about as close as you ever want to get. The reason why it's there is that there is a transition zone between the chromosphere and the corona of the sun's upper atmosphere. Why do we want to be there? Well, a man by the name of Hans Alfvén won the Nobel Prize in 1970 by saying that he figured out or theorized that the corona was a lot hotter than the surface of the sun. And the reason why is that the energy was coming off the sun went through a transformation in the chromosphere of the sun, and that transformation produced heat. Well, Eugene Parker had a similar idea back in the 1960s, but we didn't have a craft to go up there and actually test it out. Okay, so now we do, and Parker Probe is sitting at that spot where Hans Alfvén theorized. And in the last year, we've actually seen what Hans Alfvén was talking about, the transition. Okay, it used to be thought that the sun's surface heated up the corona. The problem with that, the surface of the sun is about 5,800 Celsius. The corona can be about 18 million degrees Celsius, right? So thermodynamically, something that cold can't make something that hot. So there had to be something else going on. And this transformation that Hans Alfvén kind of theorized about, as well as Parker, has proven true. Okay, so this is our sun. Our sun rotates every 28, 29 days. Okay, most people don't know that. The first person to actually prove that was Galileo in looking at sunspots. He saw that the sunspots changed spot, but they didn't elongate. So what happened was that he came up with the idea that the sun actually rotated. So this is a view that you're going to see in my telescope. It's red because we're looking at the red light from the sun, called a hydrogen alpha telescope. This one happens to be not hydrogen. This is one of our satellite images of the sun. And we take pictures of the sun all day long in different wavelengths. This happens to be the ultraviolet region of helium, but it looks just like the hydrogen alpha view that you're going to see in the telescope. And you see there's all sorts of things going on. You got this stuff up here, okay? And you've got this stuff that's down here. The other thing that you should notice is not flat red. It's got texture. There's a surface to the sun, and you're not taught that in school, okay? Because it's not a surface like you're used to, okay? It's denser than a gas, but it's not quite as dense as water. But there's a skim to it, okay? That's because the sun, all stars are made out of plasma, okay? And you can see that as you watch what's going on in the sun. You get splashes, you get clouds, you get evaporites that are coming up here and they're starting to condense. So what we do is we make an analogy, okay? On the sun, just like on the earth, these would be called clouds. They're not made out of the same thing. It's not going to rain on the sun. If you ask a 5-year-old, will it rain on the sun? They will tell you just intuitively know it's too hot on the sun for that to happen. So these clouds are made out of plasma. They're not made out of water vapor. And you can see them all over the sun. Okay, these are active regions. And if we're real lucky, like over here, we're going to get a solar flare out of that. Okay, now it opens up all these questions that people have about why the sun does this. And I said the reason why we study the sun is a star. We learn about our sun, we learn about other stars. So once again, it's an analog of looking at everything you see in the night sky. Some are bigger, some are smaller, but basically, this is what we know about stars. All right, now this is where it gets a little bit complicated because when you say the sun's made out of a plasma, first thing they think about is when they went to the hospital and they got, you know, some kind of blood treatment and blood has plasma in it, right? Well, it's not the same kind of stuff, okay? Plasmas are ionized materials, okay? They're at very, very high temperatures and gases don't work well under those conditions. So everything you see on the sun is more like a fluid than it is like a gas. Okay, and how do we know that? Well, this big, huge word here. The sun is a magnetic hydrodynamic object. What does that mean? Well, magnetic, in other words, there's a lot of electricity going on with this thing. There are charges involved, pluses, minuses. Hydro, it acts like a fluid and it's moving, it's dynamic. Okay, so that's what that big word means. Don't ever try to do the mathematics of that. Okay, the mathematics of MHD is way up there. Okay, you have to integrate 5 equations all at once to be able to get the answers that Eugene Parker and Hans Alfven were looking at. Okay, so this is a good view of the sun. This time it's ultraviolet light, and it's the ultraviolet emission of iron, one of the species of iron. Okay, and you can see all this interesting activity, solar flares. You see these clouds of plasma being pushed up in the atmosphere of the sun. And this really opens up more questions now about what that is what's going on there. Why is that staying there? If the sun's a gas, how's that staying that spot? Why doesn't it just drift off? That's because it's magnetic, it's a fluid, and it's moving. Okay, you know about plasmas, but they don't call it that when you go to school. Okay, when you have some kind of lightning storm, okay, the electricity goes through the sky and it plasmatizes the atmosphere. Okay, it ionizes the gases and they act like a fluid, they flow. Okay, most of these other kind of things, you probably will never come in contact with them. Lightning, you will. If you look up and when we have some solar storms, like we've had in the Philadelphia area last May, people got incredible pictures of the aurora right here in Delaware County. Not only did we see the green aurora, which we normally see, but we saw reds and we saw some blues. Okay, so aurora is a plasma. It's ionized upper atmosphere of the sun, the Earth, which we call the ionosphere. Most of the baryonic matter that we have in our universe is in the form of plasma. A little bit will cool down and it will start clumping together. And that's where we get stars and planets and galaxies. When the non-ionized material comes together because it's cold and it forms the kind of things that we see in the sky. I need to kind of preface what that means is that you and I only see about 13 or 14% of the mass of the universe. And most of that we can see is in the form of plasma. Okay, the reason why I had to preface that is that dark matter and dark energy, as we stand now with our understanding of the universe, makes up most of the universe. But that's not baryonic matter. That's not you and me. And in space, all the stars that you see in the sky are big balls of plasma. Okay, the sun has a structure, just like a planet. Okay, it's got a core, it's got some material around that core, which travels at a different velocity. That's what we think causes a magnetic field. There are some of these things that don't quite fit this model, and we don't know too much about how magnetic fields form, but our best guess is there's a core of one material, and there's a core, around the core is a different kind of material, a different density, and is traveling at a different speed. That's how our sun gets its magnetic field. When you look at the sun, you do not see fusion. You see the end product of fusion. Okay, all the fusion takes place at the core, and then that radiates out energy and light. Light is made down in here, but it bounces around. So when you take a look at the sun, you're looking at light that started here probably about 1 million years ago, because it bounces, it gets reabsorbed and gets re-emitted. And then it comes up to an area where it changes its direction and it becomes cyclic. We call that the convection zone. So everything kind of gets round together and you start moving toward the photosphere, which is the surface of the sun, which is right above this area where everything is going up and down. Okay, that's heat and electricity, both. Okay, little surface here called the photosphere. That's where light actually leaves the sun. And once it leaves the photosphere, then it's roughly 8.5 minutes before it hits the Earth. So you're looking back at time when you look at our sun and all stars. You know, most stars are really far away. So these are like time machines. Okay, up here is the chromosphere. This is where the electrons are freer and they can actually jump up energy levels. And when they release their energy, that's when we see color. That's why you see the word chromosphere here. So we take a spectroscope with us when we go to doing events. So you can actually look at the sun and pick out about 50 to 55 elements on the sun. Some of them are in the ultraviolet. We can't see those, right? So we can see the light from these atoms. And the first question that comes up, well, we've got 118 elements on our planet. You know, why does the sun only have 66? Okay, well, that's the nuclear story, right? So the Earth and stuff, it was left over from what didn't go into the sun. Okay, I always kind of personalized it and said, well, the sun couldn't use it, so it just kicked it out. And that's what became the planets and stuff like that. Well, little kids say, well, okay, I understand that, you know. But anyway, that's our general idea of what stars are. And all our fusion takes place in here, and our sun is small, and the only thing it can fuse is hydrogen and helium. Toward the end of its life, some helium into carbon, but that will be the end product of our sun. Our sun can't make any other element. Okay, so it's not going to blow up, and it's not going to make you and me. Okay, we have to wait for some big star to blow up to make you and me. The corona is something that we really can't see unless you have special instruments. However, when we have eclipses, this is a really great time to see the atmosphere of the sun, the corona, the crown. Okay, this was taken the last eclipse in 2017. It's one of the highest definitions pictures we've had of the corona. You see the poles, North and South Pole, the equator. The equator is where the slow solar wind comes from. It pushes material out into space. When we get up to the poles, that's where the fast wind comes from. And the interesting thing about the fact that the sun is a liquid, that these two can interact and you'll get tumbling of the plasma coming off the sun. Gases can't do that. Okay, so one of the things that Parker Probe actually saw was looking at this kind of activity where the fast wind is hitting the solar wind. And we saw some very interesting waves at that you could pick up, a big long name for those things, but it's a Kelvin wave. And Kelvin waves are tumbling actions that take place when you have fluids at different densities at different speeds. So this once again kind of proof that we're looking at more of a liquid than we are a gas. Okay, what a cool thing is I'm a spectroscoper by training, all right? So I just love spectroscopy. I think that's the key to anything, to understanding about material makeup. So what we did in 2017 is that we looked at the sun's corona with our spectroscope. And most of my doctoral work was on species of iron in Earth-based material or processes. That's why I was picked to be on the Spirit team on Mars, because Mars has a lot of iron on it. Okay, and we wanted to understand where that iron came from. So from a spectrographic point of view, looking at different species of iron can give us a story about where the material came from. So what we picked up, were different species of iron that don't exist under normal conditions. Okay, these are very, very high temperature. So we can use iron species to act as a like a geothermometer. Okay, and see, there's another one here, is iron 20, only happens at about 18 million degrees. So we can see these spectral lines of iron, and it will tell us, what the different temperatures of the Earth's, the sun's environment is. And it really gets hot as soon as you leave the Alphen interchange. Heats up quickly. So what happens is electromagnetic energy now, EMPs, is changed over thermal energy, and that's what seems to heat up the corona. Not the fusion inside the sun, but this changeover from electromagnetic pulses to thermal pulses. Don?
So Roger, are you looking at the limb of the sun? So you're actually looking at the profile as it's going out from it, or are you looking straight down onto the sun? Because there is a temperature profile in the chromosphere, right? So
Oh, this is during the eclipse. So the moon acts like a coronagraph. In other words, it blocks.
So this is during the eclipse.
Yeah, this only during eclipse. You can't see this because the sun is just really too bright and it washes out the corona. So during eclipses, people say, well, why do you want to go look at an eclipse? That's a pretty thing, right? No, there's some real science. And we didn't know some of this stuff until the last two eclipses. Okay. And one of the jobs that we had at Madras, Oregon, was to train our spectroscopes. Okay, we had one, NASA had a whole bunch of them, and we combined our data, and we came up with this idea that we can use the iron species to tell temperatures. Well, if we can do that on our sun, then we can use that to tell temperatures on other stars too. So everything that we learned about our sun is an analog of something that we can use to look at other stars. So it says during eclipse time. Oh, if you want to read a paper that really makes you like swim, read Moreau's article about this. This is what came out of 2017 eclipse. okay, what are these things that we see on the sun that you're calling a cloud? Yeah, we're at the craters of the moon after the eclipse, and we're showing the people, there were thousands of people, craters of the moon. And we set up our scopes, and Linda was standing at the hydrogen alpha. I was over boring people with spectroscopy, right? So this little guy comes up to Linda and he says, well, you're looking at filaments on the sun. Now, the French saw some of these filaments on the edge of the sun. So they called it a promenade, which into French means arch. So these were filaments that were arching. Well, back in the day, we thought those were two different kinds of things, but they're all filaments. But what's happening here is this filament is just traveling along the surface of the sun. So they're the same thing, and they're held down on the sun by electromagnetic forces, and it's just one of perspective. So Linda says, well, we have clouds on the sun. Well, this gentleman goes, oh, no, there's no clouds on the sun. So Linda says, well, they kind of act like clouds and, so forth. No, they cannot. He turned sideways and it said Harvard Smithsonian Center for Astrophysics on it. So she holds up her hand and says, okay, well, you got my elementary version. I'm going to give you the PhD version. And so I came up to him and I said, okay, you've got a 6-year-old come into your telescope and you say, what you're seeing are impulse-driven condensates. And he looked at me, he said, yeah. I said, to a 6-year-old? And he went, oh. He spent the whole day with Linda looking through the hydrogen alpha scope and listening to what she had to say about the sun. So it was kind of a learning moment, and we had a good laugh about it. They came back the next day too, to do it because we had all this stuff set out there. And I said, this is how you do outreach. Okay, when you're talking to your graduate students and they're going to be teachers and things like that, you can't go into a classroom and use this terminology. You lost them immediately. You got to take it from where they are and bring it out. Now, can you get to this point at outreach? Yeah. If you're listening to people that are coming up to you, you're going to get a general idea they've got some background on it. And so what we're seeing is condensation of the plasma. Okay. And that gives them a context to what's going on up there. And once again, here's this nasty term. I did some seminars with Eric Priest from St. Andrews College, who was basically one of the first proponents of MHD back in the early 60s. He gave Parker the mathematics to be able to do a lot of his theories. Okay, it comes out of MHD mathematics, which they do not teach in the United States. So most people who do MHD are coming to us from China, Russia, and Europe. And the important thing about that is that we're trying to reproduce the sun in our laboratories. We're trying to do fusion, okay, because it's cheaper than coal, right? All right, the problem is that Livermore was tackling fusion from a gas point of view. So they were trying to heat up gases to 18 million degrees to be able to get a sustainable fusion reaction. Well, gases don't have turbulence. Fluids do. They couldn't sustain a reaction. So then Europe are starting to get some headway because they're using MHD. And Livermore decided to change over. So they were going to now use lasers to increase the pressure inside the tokamak, which is the nuclear machine that we are trying to contain fusion in. And using Z-particle lasers, they could increase the pressure, not the temperature, but increase the pressure, which makes the temperature go up automatically. And they're starting to get fusion reactions. They're sustainable. The people at Purdue and Notre Dame, I think I had the world record at 2 minutes for a sustainable record. And the Chinese now have been able to do it for not only about 8 minutes, but they were getting more energy out than they got in. The guys at Purdue did not do that. They got the reaction, but they were still putting energy into it. So it's a race to try to get fusion under control. Okay, good picture of what a solar prominence looks like. There's an electrical field, a magnetic field around this active region here. The plasma goes up because it's got a charge on it. It's going to stick on that magnetic field line. Okay, most people kind of understand what a magnet's all about. So some of the things you can do at an outreach is have a magnet and some iron filing and show the kids the pretty little structures that those iron filings do. It looks just like that, okay, for the exact same reason. Okay, so prominence and filaments can happen anytime on the sun. Okay, flares, on the other hand, have to have a certain kind of environment, and you don't get flares on the sun all the time. Okay, once again, reality versus theoretical construct. Okay, the magnetic field lines of the sun. Okay, in textbooks and stuff, they show you something that looks like this. Well, what did Parker probe see? Did not see that. It saw these things. So we now refer to these as sheets. They're flux sheets or magnetic sheets of energy rather than loops. Okay, but constructually, what we have to do is we have to think this, but it's really that, because you and I have a hard time dealing with that kind of mess. Okay, our mathematics works pretty well if we deal with them like that. Okay, I like spaghetti. Okay, and this is what holds down the filaments. Okay, once again, this is coming out of the research that's coming from not only our Parker probe, but the ESO, the European Space Agency probe that's up there. We're actually seeing that these things are controlled by magnetic interactions on the surface of the sun, most of them coming out of sunspots. Okay, and they're holding these things down. And when these things fail, these clouds can actually fall down on the surface of the sun. When that happens, we tend to get flares from it, because when that material falls down into the sun, it breaks the surface tension, and the magnetic field lines, the energy from the sun, can just be released, okay, causing something called a coronal hole. Okay, so these are being held down. This is the normal flux from the sun's surface. But when we get in this area here, we start getting these loops. They're called magnetic loops. So when a kid says, what holds them up there? Why don't they go flying away? Well, they're being held down by electricity. Okay. Can gas do that? And the answer is no. Okay, fluids respond to this. Gases don't, they'll just float around. Okay, what's the sun made out of? Okay, this is the spectra of our sun. And every one of those black lines are produced by electrons around atoms on our sun. And this is the way we do most of our science. Well, I'm a spectroscoper, right? So, okay, this is how we do science, right? So the sun's really bright, okay? It lets those electrons jump up and down around the nucleus of the atom. We used to think that light was produced by the atom. But then when Niels Bohr started talking about quantifying the electron energies, found out the light was coming from the electron. It wasn't coming from the atom itself. We get radiation, nuclear radiation from the protons and neutrons, but the light is coming from the electrons themselves. So this is what the spectra of sun looks like. And what we do is we have students and other people come up Even the guys from CERN like this. This is something they did, right? So these are absorption lines. The reason why we don't see bright lines coming from the sun is that the sun's 94 million miles away. Okay, by the time this light leaves the sun, it's going to interact with other atoms that are going to gobble up that light at that specific wavelength. So we have sodium atoms in space. So when the light from sodium from our sun produces that light, it goes out and it's at the same frequency those atoms are at, and boop, that light is absorbed. And that's why we have these black lines, which is a whole lecture into itself. What color is the sun? And the answer is whatever you want to pick. It depends on what you're looking at. By science, our sun is a G-class yellow dwarf star, even though just Monday, pronouncement from NASA is that we have a white star. You listen to Niels deGrasse Tyson. He says, we have a white star. So I sent him an email. I said, when did our sun become 10,000 degrees? He said, smart ass. I've known Niels for, 50 years. So anyway, he said, you're making it too technical. I said, no, I'm not. I'm being scientific. We have a yellow star because its surface temperature is about 6,000 Kelvin, right? You can't, mess people's thoughts up with us. The reason why we see it as white is the fact that we blend all the colors together, and that's white light. Okay, we don't have a white star. We have a white-looking star, unless you were a bee. If you were a bee, you would look at the sun, you would see blue. So what would you say? Oh, well, we're not bees. I said, but there are bees. So you'll see what your brain tells you it wants to see. So what we do at the SDO, the Solar Dynamic Observatory, we have spacecraft up there looking at the sun in different wavelengths. Most of them are in ultraviolet. Okay, so all these pretty colors aren't spectral colors of things you see on the Earth. Okay, these are high energy ultraviolet elements. Most of them are iron. And I kind of give you an idea why we look at stars with iron. Okay, and once again, we're in a modern era, but NASA people still use angstroms for numbers. Okay, so this is 450 nanometers. Okay, for those of you that want to deal in the metric system. Sunspot, what's a sunspot? Okay, this is where Galileo got in a lot of trouble, right? The word he used for that in Italian meant rotten hole. Well, the church doesn't like that. Okay, we can't have a sun that's got rotten holes on. Okay, so he had to change the word to punta, which translates as spot. Okay, the Spanish word is a lot better for this. And being from New Mexico, it was great to talk to kids in Spanish because you go, manchas solares. Manchas means smudge. So this looks like somebody had a dirty thumb and put it down and moved it across. They could understand manchas really well. American students have a real hard time with calling that a dot. Okay, and they change. There are magnetic storms on the sun. Okay, but he didn't know that. And he told us that the sun rotated by watching these things and making very, very detailed pictures of these sunspots on the sun. How big is that sunspot? Another big question. So you have to kind of get an idea in your mind based upon your focal length of your telescope. How big is that dot? Okay. In my telescope, something that's a little bit smaller than a pencil eraser is about the size of the sunspot. Okay. So here's a sun. Here's a sunspot. Now, it looks like that's a sunspot, right? Well, there's different classifications of these sunspots. They call them the WOOF diagrams. Very, very complicated. Okay, so this is a beta, gamma, delta sunspot. Okay, but it's one sunspot. And to give you an idea of the sun, of the Earth, okay, so this sunspot is 1, 2, 3, 4, 5, 6, 7, 8 Earth diameters large. We did an event down in Alamogordo, New Mexico, and we had a sunspot that was larger than the planet Jupiter on the surface of the sun. People were forgetting about the eclipse. They said, look at that sunspot. Again, when you look at a telescope, boom, you get these little black dots on the sun. It wows everybody. Look at that, They're thinking they're going to see like a red ball that's one color. This is what one solar cycle looks like. It was the last cycle. We're in cycle number 25. And they started back with Richard Carrington in England when the sun did the most powerful thing that it ever did that we've been able to observe. Okay, the first case when somebody was actually killed by the sun. If you happen to be a telegraph operator and you touched the key when this storm hit, you had some problems. Okay, not too many people died from it, but because we didn't have much electricity back at the beginning of the Civil War. Okay, that was the last time we had a really big storm on the sun, and we're overdue. That's why we're studying the sun, right? So this is a whole year. Okay, so what do we have? Here's the equator of the sun, okay? And sunspots move up toward the pole and stop. They move down to the pole and they stop, and that's the end of the cycle. So it happens over about 11-year period. Okay, so people learn in school that the sun has an 11-year sunspot cycle. But we also have a 22-year cycle. We have a 100-year cycle. So we have different cycles now that we're getting more technologically understanding about the sun. Okay, a lot of different kinds of cycles. What we do is predictions, when the sunspots are going to happen, when we're going to have the most sunspots. We call that solar max, right? So they predicted that solar max would be here in somewhere between 24 and 25, and that would go downhill. That's what they predicted. So this is a smooth curve here. This is a daily kind of record. So they have these bars called error, and we get this little hump. That's a sunspot cycle. It starts, it gets a maximum, and then it ends. And this sunspot cycle was supposed to go until like 2030 something. Wrong. Okay, so what has happened on our sun? And all these things are available free of charge. I have a friend down in Atlanta that works with the Observatory of Belgium, and his job is to put together a daily record of sunspots, and they put that in chart form. And here's the northern hemisphere peak, here's the southern hemisphere peak, and this is what's happening on the sun. And we're not in the 25 yet. I mean, we are just in the 25. So the maximum period of time hit in about October and has been slowly tapering off. So solar maximum is over. What's happening down here? Well, I haven't seen any predictions yet. Will it go to 2030? Oh, probably not. How do we know, besides looking at the graph, how do we know when we're going to get a sunspot cycle change? Well, this is where it gets a little crazy. And the fact that you and I see this, all right? A magnetometer sees that. So this is polarity. sunspots have a polarity. This is positive north, this is negative south. So every sunspot cycle has a preferred polarity of the sunspots. When you look through a magnetometer and you see negative over here and positive here, we're starting the new cycle and they overlap. So sometime in 2026, 2027, we're going to start seeing a mixture of these magnetometer readings. And you can go on the SDO site and see the daily magnetometer readings. So you can kind of do your own predicting about when the sunspot cycle is going to begin or end. The one we're in right now overlapped with sunspot cycle number 24. 24 didn't end until about here. That doesn't usually happen. Usually one ends, you have a quiet period of time, then bang, you start the next one, right? These lingered. So we had plus minuses here and minus pluses. We had a mixture. And that's the reason why this cycle is more energetic than it's been. And it was predicted to be less than cycle number 24. Okay, once again, kids can look at graphs. People can look at graphs and see trends. This is what I call the magnetic field lines. Once again, our friend, the magnetometer, will show us this image. So they have a polarity, they have a north and south, okay, and they come up like that. And the plasma from the sun will stick on these things, and that's what causes the filaments that we see on the sun. But remember, we don't see this one very specific line. We see a sheet of electromagnetic energy. And look at this, an area where there's not a lot of that spaghetti going on. That's called a coronal hole. Okay, with my H alpha, I can't see those. I can infer them, but I can't actually see them. You've got to see them in a higher wavelength. Now, what causes a sunspot? As I told you, it was a storm on the sun, but how do storms start on the sun? I mean, is it on the surface, on the underneath? You know, what's going on there? This is something that the Navy Research Lab came up with, and Dave Hathaway turned it into a little cartoon, in that the first time we've actually seen energy coming from underneath the surface of the sun. So sunspots form under the surface of the sun. They don't form on the surface like a tornado. Okay, it acts like a tornado, but it starts underneath the surface. So there's a lot of twisting going on here of these magnetic field lines. But we now have actual proof that sunspots and flares and things like that start under the surface of the sun. In a good solar telescope, you're going to be able to pick up these convection cells. Each one of these is about the size of Texas. So you have convection coming up and going back down. They come up in the middle of the convection cell and they go down. So these are cooler along the edge than they are in the center. And these sunspots form at the edge of one of those cells that we call granulation. And with a good H alpha telescope, you can see that. Okay, this is a really nice high definition view of what a sunspot looks like. And you can kind of see it's breaking from the edge of the center of this convection area and then falling back down. And this is one of your favorite pictures, Don. This is called a light bridge. So you know that there's going to be a flare pretty soon, because the polarity here should be north-south, but what we're seeing is a mixture of the polarities. And this means that we're getting a lot of twist going on with that That's a precursor to a solar flare. Okay, so we have the northern hemisphere here. Well, how do we know what's north and south? Well, it depends on what, where you are in that 11-year period. At the end of the 11-year period, this is south and this is north. At the beginning, this is north and that's south. The sun actually flips its poles. It doesn't turn upside down. Our planet does the same thing. The sun does it every 11 years. The Earth does it every 800,000 years. And we're in that period of time right now. And nothing in the equator. So this is a process called movement toward the poles. Sunspots start somewhat above the equator and they move north and then they stop and the cycle ends. So that's what it looked like 2 years ago. And this is what it looked like in October. Now the sunspots are bigger in the north, but there's a lot more of them in the south. So the sun acts differently depending on what hemisphere you look at. We didn't know that. Okay, climate change. Is the sun responsible for climate change? Okay, the sun's getting hotter, therefore the earth's getting hotter too, right? Okay, we're in the middle of a cycle where we're actually getting closer to the sun. Okay, it's called a Milankovitch cycle. So we're coming out of an ice age 18,000 years ago, right? So we're halfway in the Milankovitch cycle. So that's what's causing global warming, right? Well, let's take a look at the data. Okay, here's the projected temperature of the Earth, and people have a hard time with this. There are some errors in there. Let's not worry about that. The Earth is warming up. That's a fact. What's causing it is the thing that's kind of conflicting. The Earth is warming up. This is the solar energy of the sun. It hasn't changed much in millions of years. Okay, if you take a look at these numbers, these are watts per meter squared. So we don't actually even go 1 watt per meter squared different over the history of our sun. It's really stable, which is a good thing, right? We live here. We don't want the sun getting really active sometimes, right? Okay, so when we're looking for new planets, one thing we're looking for is how about what's going on with the energy of that star? Okay, does it ever affect the Earth? And the answer is yes. But the last time it happened was in the 1600s. We had no sunspots for 75 years. The Earth's temperature went down. All the rivers in Europe froze. Okay, that kind of climate change, right? Okay, but climate change is something that happens over thousands of years. So the weather changed when we had no sunspots. As you see, we've got some areas where we have small sunspots, some where we have a lot. Remember, the solation of the sun basically stays the same. Here, it actually went down, but that's a 75-year period of time. And that was called the Little Ice Age. You can do all sorts of cool things, do some research about what Europe looked like during the Little Ice Age. And here's people actually skating on a river that was supposed to be liquid at this period of time. This is an interesting thing. We just found out that the sun actually touches the Earth. Okay. Back in 1908, a guy by the name of Birkeland theorized that the sun's magnetic field induced a current in the Earth's ionosphere. He was laughed at because he said the sun was made out of iron sulfide, which it's not. Okay, but this is correct, but they didn't accept it until a few years ago. Alphen and Parker both felt that Birkeland was correct. Birkeland was Alphen's department chairman at the school that he went to. Okay, so he was right, and we just found that out just recently. If we had kind of listened to it back in 1908, maybe it would be a little further ahead than what we are. So the sun actually touches the earth. There's an interaction between the magnetic fields. And you can get some detail here about what Hall currents are and Pedersen currents are. There's a whole realm of information that you can get from this. But you don't do that in outreach. You don't have the time. Our happy aurora, right? This happens to be in Oregon someplace. What are we seeing? Okay, I'm a spectroscoper, right? So when you look at the aurora, you're seeing a spectrum. What are you seeing the spectrum of? It's the element oxygen. Okay, we don't see the blue from nitrogen very well where you and I live. Okay, this is you see the nitrogens, way up in the Arctic, not too far away from the polar regions. Okay, this is another thing. They take a look at the filaments and say that they're flares. No, they're produced by flares. So the flare is this energetic eruption that takes place on the surface of the sun. It throws the plasma up in the air, gets caught on the magnetic field lines, or can be blown off into space. And flares are like earthquakes. They have a rating system for them, all right? So X-class flares, which is the one that's right here, are the most energetic kinds of flares that we have on the sun. And unlike earthquakes, there's no upper limit to an X-class flare. All the other classifications are logarithmic based on 10. Okay, but once you get to an X-class, there's no upper limit because we're dealing with a liquid, not a solid like on our planet. Okay, once again, you can talk a lot about, what kind of solar flares are going on. Okay, look ahead of time. See if there's some C class or A, B class or whatever. It's something you can tell the people. And this is the largest flare that we've ever observed, which means we had to be looking at it with instruments to be able to figure this out. So it's not the biggest thing that's happened in the history of the Earth. We didn't look at the sun until fairly recently. So this was an X-class 40, which we haven't seen for a very, very long time.
Roger, what was the character of that estimated speed?
Well, there were some problems with the flare itself because we had 3 CMEs at the same time, and we had flares at the same time. So the individual flares were estimated to be in the 20 to 30s, but you had like 2 of them go off at the same time. So it was a big event.
Yes.
Okay, yeah, you can wow people with numbers. Okay, the number up here that I find really interesting, that in one solar X-class flare, it's 20 times the world's consumption in a year. So all the Earth producing energy for 1 year is in one X-class flare. If we could harness that, think about the unlimited amount of power that we have. Why do we care about storms on the sun? Well, this is what it can do. energy from the sun can come down and come into our poles. It can hit transmission lines, and this one happened in Canada. It took out a power station, which now blew up a transformer, which blew up another transformer, and the Canadian grid went down. New York City was without power. Okay, that happened today. Like the Carrington event, the United States was without electricity for about 5 years. That's the reason why we want to study what's going on in the sun. And Parker Probe is giving us information that we can predict when these things are going to hit. That's the main goal, predicting solar storms. Right now, we're about 72 hours. The grid operators want 24 hours. So we got a long way to go. So what happens when this thing knocks out a transformer? So this damage was done in 92 seconds to a number of transformers in the Canadian grid. Luckily, these are fairly new. So the Chinese had a few, Britain had a few, we had a few. So we got the grid back up in a couple of days. Okay, some of the grid transformers in Iowa were put in the 60s, and they're not even made anymore. So some of the money that should be going in to transformers gets pocketed and they never upgrade them. So we're way behind in upgrading our grid system. Now, this is where it gets a little bit squirrely, and the fact that what Alphen is predicting is that we get a change from electromagnetic energy into thermal energy. But how does that happen? Well, this seems to be the culprit. It's called switchback. So what happens is that we get a normal line, magnetic field line, interacting with another one, and we get this little kink in the magnetic field line. When that kink happens, it gets propelled upwards and then it breaks. And it happens to break in the Alphen convection zone or the interaction zone. We're thinking this is responsible for heating up the corona. The kinks in the magnetic field line. This is another representation of what that looks like. The normal field lines here, we get them recombining up here. And then as they do that, they break off and get shot up in the atmosphere of the sun. For some reason, the physicists in the United States used the word reconnection. Alphen was livid at that term. He said, nothing is reconnecting. It's already been connected. It's just changing. So, you know, he had the Nobel Prize, but the news media kind of beat him to it. So the term reconnection is kind of misleading. So it's not reconnecting anything. What it's doing is it's transforming into something else. And this just came out of the people I work with, which is Goddard Space Flight Center. Okay, this is an actual computer simulation of what actually happens in a sunspot. The energy goes down in between the granules. The sunspots are formed in the middle, and that's where all this kinking of the magnetic field lines takes place. So as you see these little switchbacks going on, that's what's causing the solar wind. That's what's causing heating up of the corona. This gets really elaborate, but what's happening is that the magnetic field lines go back down on either side of the sunspot. In the middle, they start to twist. That's what's causing these kinks. CMEs you hear about all the time. What are they? They're the most energetic thing our sun can do. And they don't produce a lot of gamma rays. Very, very few. Mostly it's in the X-ray range. But it's also throwing off matter. So this stuff rains down on the earth. And it rains down, doesn't happen immediately, okay, because it's matter. So it takes longer than 8 minutes for it to get down here. So generally the time frame is 24 to 36 hours. CMEs are held together just like the filaments are. They've got these currents that wrap around them, and those currents break and once again reconnect. They don't. All they do is they potentiate. So the top of it actually breaks off and that gets shot out into space. What you're hearing are the microphones on the Parker probe. That's what a CME sounds like. And this thing is kind of the workhorse of Parker probe. There's 6 inches of nanotubing, which the equivocation is about 20 miles of material. That's why the let's go on. Let's go on right there. Okay. Look. There we go. So as you see, there's a lot of information about this, and you can go into a lot of detail, but remember, you got 3 to 5 minutes. And you got young people that are not familiar with some of this stuff. Okay. And you never know who's going to come to your scope, a guy from CERN or somebody from Elwyn. Okay, so you got to take the people that come, find out where they're at, and try to give them something to take away for it. Okay, so that's my idea of how you interact with the public. Another way is to get them involved in doing citizen science. That's you.
That's me, okay.
Okay.
The mics up there.
Yeah, let you do your thing and then we'll do some quickie questions. and
All right,
do that.
sounds good.
Right?
So, you know, I'm a big fan of citizen science. And so when Roger said he was going to do this talk, I said, why don't you add some in for solar science? And so he did very nicely. So this is the QR codes if anybody wants to scan these so you can actually do it. The nice thing about citizen science is that you don't have to be a scientist by training. If you are, you may be a scientist in a different field. Still, it's fun to actually do it and you're actually contributing to real science. So this is one sunraiser where you're really finding new comets. And actually a lot of new comets, over half of them have been discovered this way by people looking at these images and finding them. So it's a pretty fascinating thing. This is actually evolved with the Navy. Another one is the auroral zoo, and looking at really understanding how the sun's energy has transferred to our atmosphere along the lines of what Roger's been talking about here. And you're going to be characterizing different auroras. There's amazing shapes of the auroras. It's not just standard ones like you see, they can be very dramatic. So this is one where people can really help with that sort of work. Another one's just sunspot detectives. You know, we have a lot of historical data. Roger's alluded to some of that. And over the centuries, people have been looking at the sun and making wonderful drawings or pictures of them. And so they're asking you to actually help with looking at some of these historical things and actually helping to characterize them so we can see how things have been changing over the centuries with the sun to add to our current data sets. And that's all basically I had at that point. Okay. All right. Thank you. You're welcome.
Now, do you all have any kind of general questions or specific questions, depending on how much detail? And same way, people at home, if you have questions, I'm not quite sure. I think I can hear you, right, Don? If they have a question? Okay. Yes.
had the privilege of looking through your solar telescope when you were in front of the student center here, and it was truly amazing. So my question is that I understand the eidolons, I understand the different kind of filters that go into it. There are still sold Herschel wedges.
Yeah.
Where do they fit into the arsenal ways that we have of looking at the sun? Do you use them? Do you like them?
Apples and oranges. Herschel wedges give you a view of the photosphere. Just like a Thousand Oaks filter that you put on the front of your thing. Oh, thing about Thousand Oak filter, anything that sticks on the front end of your telescope, really look at that. Because every time you take them off and rub them, you're taking material off of. So, you know, look at those and see what you're doing to the beta film. The ones from Thousand Oaks are glass, but the glass can actually be degraded too. So what you do is take it off and look at the sun. If you see any light coming through them, get another one. Gotta be real careful with that. So there are big telescopes that use Herschel technology. And what they do is they still draw the sunspots with that. They, when you're looking at it through hydrogen alpha or calcium or whatever other filter, you're not going to see the sunspot development like you will if you're looking at the photosphere, because you're looking at black and white. So they're real obvious at that point. So they do have a place in solar observing. The bigger telescopes in our country are what we call photospheric solar telescopes. Okay, the one at Mauna Kea is a filtered one, so you're looking at it in different wavelengths. But the ones in space are basically, as I said, looking at iron, ultraviolet light, and stuff like that. On the Earth, we have some problems. We have an atmosphere we're looking for, right? So hydrogen is the best color to look at. Calcium is probably the next. The problem with calcium, a lot of people can't see that wavelength. So you have to have it on a monitor, and that gives you like 4 extra pieces of equipment. So hydrogen alpha is probably the way to go with that. So to me, having a white light scope with the hydrogen alpha is like the best of both worlds. They do something different, but you put them together and you get the whole thing.
Do we know more now as to why the solar wind is accelerating? So I thought that was kind of an issue that's still unclear, right?
Well, with the switchbacks, those switchbacks you see here are kind of static, right?
Right.
They're not. They're rippling up the magnetic field line.
Okay.
I guess I need to be over here. They're rippling up the magnetic field line. When they snap and they go off at a velocity. So the slow solar wind is roughly 300 to 400 kilometers per second. The fast solar wind is like 700, 800. So they can combine. The fast solar wind can interact with a slower solar wind and accelerate. So we see that acceleration, and it's almost endless. We see the acceleration all the way out to the edge of the solar system. We just happen to be in the way. A lot of people get the idea that the sun is only doing this for us, right? It doesn't even know we're here. You know, it just happens, and we happen to get in the way of that. It's not like dark energy per se. We don't know how dark energy accelerates things. The new image that we just got from ALMA shows more granulation in the background energy. Okay, and it's more granulated than it was before. You know, we see little areas where it's going at one velocity and then it speeds up, it slows down. We have no idea. Well, we don't know what it is yet either, but we know that it accelerates it. And with a solar probe, Parker, able now to actually measure, quantify this switchback. And it happens exactly where Parker and those guys theorized it was happening, right at the intersection of the chromosphere and the corona. And it's a big difference. I mean, it's, you know, many EMP numbers up. So there's a lot of energy that's taking place there.
Question, you mentioned about the Carrington event, and in terms of studying those things in the Earth's past history, there's been, I've read some articles that have said that there's ways of looking at tree data and things like that to be able to determine that there've been other events that have been even more serious than the Carrington event in the Earth's past. So, you know, you mentioned about how serious that would be if the Carrington event occurred today. What about, I mean, these other events, how much more larger were those events, say, compared to the Carrington?
Yeah, when you take a look at what we call proxy data, there's a Japanese scientist that has done a lot of research on that by doing dendrology of, you know, trees and things like that. When trees are growing, they're absorbing carbon-14, all right? So you can take a look at the width of the tree rings and so forth. During these events from the sun, it comes down and hits carbon-13 and turns into carbon-14. So there's a lot more of it during these events than there are normally. So if you see differences in the diameter or the thickness of tree ring, you know that the Earth has gotten some kind of energy from someplace. Gamma radiations or gamma bursts are recorded a little bit differently in the dendrology than the carbon-14. So you have to look at another isotope, and generally it's boron. But you can find those in the tree. You can find it in going back and look at artwork, because people have been on the Earth looking up at these events, and they've recorded it, you know, either in caves or, you know, in this case, like I showed you, on canvas. So you can go back and look into that. So you can find it in rock. You can find it in strata of soil. You can find it in deep sea cores, especially looking at different isotopes of oxygen. Okay, big uptake in, you know, like oxygen 19 because of solar energy. So yes, there have been really bad storms that dwarf, you know, what we have today. A lot of suns get a little bit older. Okay, so does that have anything to do with it? Maybe. Okay, some stars, when they get in this stage, they get real energetic and they start putting off more stuff. We don't think our sun will do that. Not like Proxima Centauri, which is actually Proxima Centauri B. Proxima Centauri, I'm sorry. It's a lot more energetic. It's not as stable. We thought that B and C and D planets were habitable. Now we find out that these eruptions on that star would take care of life. It would just wipe it out. So they've been taken off the list for that. But yeah, there are proxies that you can study. Some of it's in mineralization of different rock. Okay, this is just a field of study. But yeah, we've looked at events, especially this Japanese scientist, I can't remember her name. They're actually called an event. And she'd gone down through history looking at soil sediments and things like that, and said, boy, these things in the past were doozy. They were bigger than the Carrington event. Yeah. Well, thank you. I know that I gave you a lot of stuff. So it is kind of mind-boggling what you have to do with it, but don't let it get you down. You do not have to be a heliophysicist to do this. All you have to do is have a good scope and pick a couple of things that you're gonna call it your own. And just do it.
And I might add that we have a lot of solar events now on our calendar, as Don Miller mentioned, that we have not had in the past. And I can tell you personally that you don't have to even have a scope to help out at these events. We just need people there, either direct traffic, man the tables, or whatever else. But one of the best things you can do there is go to the Kennedy's telescope and just take a look. Hopefully when it's not crowded, but it's jaw-dropping what that scope can show you. I own a solar telescope and I've never seen anything like it. It really is worth your time to come out to the events just to take a gander through that. And if you have a white light filter, you know, one of the ones that he was talking about, or if you even have a Herschel wedge, who cares? The point is that all of that stuff is helpful. So if you got it, come on out, give us a hand. I know that it's a lot of great fun, and that's a special scope. I don't think you're gonna see that in a lot of other astronomy clubs events. You're not gonna get the kind of view that you're gonna get through that particular piece of equipment.
And
That's
one
real
more
pretty.
thing about the Herschel wedge, they tend to be at your eyepiece
Mhm.
area. They recommend you don't have an aperture bigger than 109 millimeter.
Mhm.
Okay, so if you got a 6-inch telescope,
Forget it.
don't put a Herschel edge on that end. Okay,
Okay.
put something over the front, like some Bader film, to break that down.
I was just surprised that they still sold them, that it's just such an old technology, but
Yeah,
yeah,
yeah.
but there they
I mean,
are.
they're great for like 2-inch
Mhm.
scopes because you can get a really nice, black and white image.
Mhm. But just as a caution out there to everybody else who's out there, maybe listening or is gonna review the YouTube videos on this. Part of what is suspected why Galileo was blind in his older years was that he did a far more solar viewing without proper equipment, because they didn't even know what proper equipment was at that point, than he probably should have.
Yeah,
And
just reflection off the white surfaces that he was using.
Mhm. And it's suspected that a couple of other famous astronomers, including Nicholas Copernicus and who else? Tycho Brahe, also lost vision due to improper solar viewing. But if the equipment is proper, I think it's actually safer than just wearing a pair of sunglasses and going to the Jersey Shore and hanging out on the beach.
Yeah.
So please come out. It's worth the experience, I'm telling you. Anyway, thanks again. If Bruce would give us a quick taste of what's coming up next month for our last meeting of our academic year.
Yeah, so 2 things before we leave. First off, Roger touched upon the Parker Solar Probe. I've got materials here on the very recently launched Punch mission and a detailed update on Parker. It'll give you the history, the engineering of the craft, which is pretty remarkable, and the science objectives and some of the findings that Roger touched upon at the time of the year. So take a copy, and those of you online, if you want this, I can send it to you electronically. So just please take this. Yes, what's coming up in May, we have Julian DeWitt, he's from MIT, and his talk will be characterizing exoplanets with high precision transit methods to measure biosignatures and assess potential habitability of exoplanets. So again, very timely, kind of hot topic right now. So please come.
All right, thanks. We'll see you all next month.
Hey, Bruce, save me some of that documentation. I'll be there next month.
Okay, absolutely.
Thank you.
Thanks, everybody.
Hold that, man, all mistakes.
What you're saying about how great this was set up.
We got,
They're great, huh?
the new one that, 100 millimeter, which is, what they've done with the other one.
Nobody fed me dinner.
I can't stop them. The other one's basically bend a filament inside. And you get it back. But there's a lot of.